محمد Amin, on veut d'obtention de diplôme de doctorat en troisième cycle. Vous avez 20 minutes pour présenter votre travail dans l'intitulé études et modélisation des émissions rayonnées en champ proche champ lointain des dispositifs électroniques. Allez, 20 minutes, 30 minutes.
بسم الله الرحمن الرحيم. A member of the jury, family, friends, colleagues, Assalamu alaikum, and thank you for honoring this ceremony with your presence. Today I would like to welcome you all to my thesis defense on study and modeling of radiated emission of electronic devices in the near and the far field, under the supervision of Professor Babori, Mr. Khalfullawi, and Mr. Riyad. I'm giving 30 minutes to summarize my thesis, and I will walk through the following points. First, an introduction to the electromagnetic capability modeling. Second, an investigation of the equivalent source and plan wave spectrum methods in radiated emission modeling. Third, I will introduce a novel radiated emission modeling methodology. Finally, I will present the conclusion of the research work done and the envisaged perspectives. On March 1959, Texas Instruments has introduced one of the most important innovations of the 20th century, which was the world's first integrated circuit. Henceforth, the microelectronic industry has progressed more than 100 billion times from its origin, as evidenced by this figure. This graph represents an observation known as Moore's Law, made by Gordon E. Moore, the co-founder of Intel, in 1965, affirming that the number of transistors on an integrated circuit will double every 2 years, with a forecast of 1 trillion transistors per device being reached by 2030. Indeed, embedded systems are exponentially integrated in various technological fields, such as telecommunications, aerospace, security, medical, energy, etc. Also, as microassemblies techniques continue to evolve, it becomes now possible to realize a very large-scale integration circuit, as well as new packaging techniques, such as system-in-package and system-on-chip technologies. On top of that, semiconductor companies are leading system miniaturization onto the next level, where the antenna is no longer a printed shape in a printed circuit board, but is integrated along with the radio frequency chip in a single package chip, which is referred to as antenna-in-package, antenna-on-chip. Taken together, all these developments will further shrink the actual device in size, enabling therefore high integration densities of these devices in a much more limited space, which will definitely lead to serious electromagnetic interference problem if the electromagnetic capability is not considered at the earliest stages of this equipment development. For an example, with the case of radio frequency chip, it mainly houses numbers of amplifier, coplanar wave grid, inductors, a bandpass filter, an oscillator, and with the new IP and AOC technologies, also an antenna. The radiated emission emitted by the antenna can be coupled back to other components presented in this shape, and thus cause undesired system performance or even system failure. This implies that there is an indescribable need to study, understand, and predict the behavior of such devices. Therefore, the electromagnetic capability consideration has become a major challenge in order to reconcile the problem caused by the ever-increasing integrations and to the technological evolutions. That is to say, the modeling related to the electromagnetic capability has therefore become indispensable. A system designed with a complete disregard for the electromagnetic capability will always have problems when testing begins. As electronic products are developed, the number of available noise reduction technique will decrease. At the same time, the cost of noise reduction technique will increase. The analysis at this point to determine which of many possible noise path combination contribute to the problem may not be obvious or simple. The solution at this late stage will typically involve adding additional components that are not an integral part of the circuit. Therefore, given the number of existing electronic devices, the consequence due to potential malfunction could be severe if the electromagnetic capability is not considered. The emitted electromagnetic field from high-speed digital electronic devices must therefore be predicted at earlier stages for both design and post-optimization phases. One of the simplest prediction methods is to use an OM solver, such as HFSS or CST. However, due to the complex geometry of modern electronic components, the use of these methods becomes impractical. Therefore, the current focus of the OMC research is to develop new methodologies that allow the prediction of the electromagnetic capability at every level of a complete electronic system. That is to say, the component, the electronic board integrating component, sub-assemblies containing several boards, and the equipment group in sub-assemblies. Components at each level contribute to the smooth operations at the integration phases. During the development of a new electronic product, these radiated emission models provide system designer with a useful tool to simulate their system design and solve many interference problems before prototyping. Until now, the scientific world has not yet agreed on the methods, and there are two different dominating approaches to predict the radiation behavior of a radiating structure in the near field and the transformation in the far field. These methods are the equivalent source-based methods and the plane wave spectrum theory. What these two approaches have in common is that are both based on a near-field scan along the surface above the device under test to predict the OM field emitted in the near field and the far field regions. Although these models have been efficient in modeling the radiated emission from only near-field data, they face multiple limitations when the field prediction is considered at high plan. Therefore, having robust radiated emission models has become a major challenge in today's industry to ensure the reliability and the best performance of their product. It is in this context the research work of this thesis was initiated. It aims to study the electromagnetic capability from the emission point of view. The objective is to develop a general radiated emission model that can be applied to any type of component, simple and fast to obtain, integrable in 3D electromagnetic radiation tools, and a model that can achieve a high accuracy for far field prediction as well as for the near field prediction, and that for any given observation plan. In order to achieve our objective, we have firstly chosen to review the most widely used radiated emission model according to some criteria. Based on the analysis presented in this table, we have stated that the infinitesimal dipole models and the plane wave spectrum methods are a good alternative that can meet the OMC requirements. This is because the use of the current densities model presents the disadvantage of being time consuming and the field under the source plan cannot be predicted. While the limitation of the dipole moment model is that 2 types of measurement are required, in addition to achieve the required accuracy, optimization algorithms are strongly recommended, which will result in a high computational load. On the other hand, infinitesimal electric and magnetic dipole models are relatively less time consuming and can achieve good accuracy without employing any time-consuming optimization algorithm. Among the 3 infinitesimal dipole models mentioned, the use of the one based on electric dipole seems to be a good option because it is simpler and less time-consuming than the one based on both types of dipole and more accurate than the one based on magnetic dipole. However, for the characterization of large-sized devices, the use of the PWS approach seems to be a better choice because of its simple extraction procedure compared to other models. Based on these findings, our choice was to perform a comparative study beforehand in order to study between these 2 models in order to study their efficiency in radiated emission modeling. In this part of the presentation, we will present the comparative study effectuated. We start with a brief description of the device under test, which is an ESM band patch antenna operating at the 2.4 GHz frequency for Bluetooth and Wi-Fi applications. The antenna is fed by microstrip transmission line. Its geometry consists of a dielectric substrate with a thin thickness or transmission line along with a patch on one side of that substrate and the ground plane on the other. The antenna is designed and simulated in HFSS, where a full wave simulation is performed to extract the near field data. In the equivalent electric dipole model, the antenna under test is replaced by an array of infinitesimal electric dipole uniformly distributed in an XY plane. Each dipole of the model is characterized by prefixed parameters, which they are a negligible length and width and operating frequency and the position of each dipole in the XY plane, and parameters to be determined, which they are the orientation and the excitation current of each dipole. The magnetic field radiated at point M in the space by an infinitesimal dipole can be given by the following expression derived from the magnetic vector potential, with R is the distance separating the observation point M and the dipole center. Indeed, the total magnetic field radiated by this array of dipole can be corresponds to the contribution of each dipole at this point. Therefore, the relationship between the scanned magnetic near fields and the dipole sources is written as the following matrix system, with M as the observation point number and N is the dipole number. In order for this set of dipole to radiate the same field as the antenna under test, the orientation and the current of each dipole must be determined. Therefore, consequently, the dipole solution can be found by applying a least square immersion of the matrix alpha as follows. Thus, the unknown orientation can be obtained by applying an element division as shown in this formula, while the current intensities are obtained using these equations. Once the current and orientation vectors are determined, it becomes possible to simulate the dipole model to predict the radiated emission of the antenna under test at any distance along the z-axis. The PWS transformation properties allow the decomposition of a radiated field extracted on a near-field scanning plane into several plane waves propagating in the space in all directions and with different amplitudes. Since the medium is linear, the magnetic field is considered as the combination of these plane waves that satisfy the Helmholtz equation for the magnetic field. A general solution of the Helmholtz equation is given as follows, with K is the wave vector, R is the position vector, and F is the plane wave spectrum vector. From the knowledge of only tangential magnetic field component extracted at a distance d1 above the device under test, and by applying two-dimensional Fourier transform, the X and Y spectral component can be found using these expressions, while the Z component, spectral component, can be extracted by exploiting the relationship between the three spectral components given by this formula. Then, the transformation into the far field region, or in a plane higher than D1, that is to say, for example, D2, is accomplished using the extended spectral domain fields given by this equation. The magnetic field at D2 can be reconstructed using this expression and can be reconstructed from the known spectral component at the same height and by applying two-dimensional inverse Fourier transform. In this part, both models are applied to model the radiated emission of the patch antenna under test. The near-field cartographies are extracted in an XY plane that have an area of 150 millimeters times 100 millimeters, and it is located at the height of 3.5 millimeters. In the case of the equivalent dipole model, a 51 times 51 scan point were used to export the near-field data from HFSS, while in the case of the PWS approach, a 75 times 75 scan point were used. To investigate the practicability of both methods, numerical simulation is performed to simulate the dipole model and also to perform near-field to far-field conversion using the PWS approach for two different elevations, namely 13 and 43 millimeters. The obtained results, that is to say the modeled fields, are then compared to the reference field of the antenna simulated using HFSS. Comparison results at 13 millimeters are presented in the following figure. We can clearly see that the modeled fields obtained using both methods are identical in both profile and amplitude to the simulated one of the antenna, with the PWS approach having a slight superiority over the equivalent dipole model. This superiority becomes more evident when comparing the relative error obtained on both methods. In order to provide clear comparisons, we present a cross-section of the modeled fields obtained using both methods, along with a cross-section of the simulated fields of the antenna. The one-dimensional section crosses each magnetic field component at its maximum field intensity along the x-axis. According to the obtained results, it can be inferred that the PWS method is more efficient and reliable in the near planes above the antenna than the equivalent dipole model. Moving towards higher planes, such that of 43 millimeters, we observe a divergence in the results and the dispersion in the profile of the modeled fields obtained using both methods. We also observe an exponential increase in the error values. The differences in the field amplitude level are also remarkably amplified, as shown by this figure. In order to allow proper comparisons, the evolution of the total error of both methods is also presented in this figure. It is evident from the error evolution that the error values of the PWS approach increase more significantly than those of the equivalent dipole model. Thus, it can be concluded that the equivalent dipole model becomes more practical and efficient whenever the radiated field is characterized at far planes above the patch antenna. This table summarizes the comparative study effectuated. Based on this analysis, we can state that the equivalent dipole models appears to be the most versatile radiated emission model able to address the MC requirement. This is due to the fact that the use of the equivalent dipole model presents the advantage of being more accurate and practical at far distance above the device under test, where the user can also observe the radiated field for any given observation plan. On the other hand, the PWS approach requires the extraction of near-field data over a large number of scan points in order to achieve accuracy, which is usually time-consuming, especially in cases where measurements are required. However, the equivalent dipole model also suffers from two major drawbacks, which they are the excessive number of dipoles and the degradation of performance whenever the field prediction is considered at high plan. Within this context, we will present in the third part of this presentation a novel radiated emission model methodology in which an improved dipole model will be introduced to overcome all of the aforementioned limitations. Indeed, the use of elementary dipole to represent the radiation pattern of a radiated source is a common discrete inverse problem that is ill-conditioned. That is to say, for a small perturbation in the input data, the least square solution will lead to serious error. This phenomena is clearly illustrated by the evolution of the error as function of different dipole number presented in this figure. In accordance with this analysis, we can clearly see that for a small change in the dipole number entered, there is a huge change in the error values. For an example, the error introduced on the HX component of a dipole model based on 30 times 30 dipoles has experienced a 71% increase than the one based on 29 times 29 dipoles. Since the inverse problem we wish to solve may be ill-conditioned, the novel modeling procedure is divided into two main parts, in which the equivalent dipole model will be extracted after a two optimization level. In the first level, a suboptimal algorithm based on the brute first search principles is introduced to mitigate the inverse matrix ill-conditioning, while in the second level, a hybrid resolution technique based on the use of pseudo-inverse and particle swarm optimization is proposed to improve the stability of the dipole model. The underlying idea is based on the combination of these two methods, in which the PE technique is applied to provide an initial solution to the meta-heuristic approach, PSO, in order to start the search for the optimal dipole solutions. In the hope of mitigating the effect of the ill-posed system, the suboptimal algorithm is mainly introduced to provide a thorough search for the best fit number of dipoles and observation point and the suitable location of the dipole plan, and also to perform a numerical experiment that allows the derivation of useful conclusions towards the determination of an optimal imbalance matrix. An evaluation function that describes the total relative error is used to measure the suitability of each combination of the variable selections. For the free magnetic field component, the fitness function is defined as follows. The inverse problem is built into the algorithm body as multi-input models. The optimization procedure consists of analyzing the error for different combination of the aforementioned variables and check what combination mostly minimize the error. The suboptimal algorithm is implemented and simulated in MATLAB. Numerical results are presented in this figure for different dipole number and scan point. Unlike the conventional dipole model, in which the dipole plan surface was equal to the observation plan surface, in the proposed approach, the surface will be defined based on the obtained near-field data containing only the significant field values and ignoring the lower field regions. Consequently, the dipole plan surface represents only 48% of the observation plan surface. This step is vital in determining an efficient dipole models using as few dipole as possible. The experiment results shows that minimum error values are obtained only when n is around m divided by 2. Otherwise, the error will considerably increase. This relationship states that the interval between two adjacent dipoles should be equal to the interval between two adjacent scan points, neither too large nor too small, since the dipole plan surface represents only 48% of the observation plan surface. In accordance with this figure that represents the influence of different dipole plan locations and the dipole number on the error, it can be seen that the error increases whenever the distance between the observation plan and the dipole plan increase. On the other hand, the error reaches its minimum for a small number of dipoles when both plans are close to each other. Meanwhile, the dipole plan locations approaches more to the device under test surface for a large number of dipoles. Finally, the suboptimal algorithm output the best variable selection for a well-conditioned inverse problem, which is 24 times 24 dipoles, or 54 times 54 scan point, and the dipole plan located at the height of 4.3 millimeters. In this section, the dipole solution extracted from the first optimization level will be passed through PSO algorithm to further enhance its stability and accuracy. The initial dipole parameters to be passed through PSO are the previously fixed dipole positions. Initially, the set of dipoles were uniformly distributed in a restricted XY plan that contains only maximum field values. However, in the optimization phase, this plan will be extended to a larger plan that completely includes the entire observation surface. The main idea behind optimizing dipole position is to place as many dipoles as possible in the most interesting field area. The other parameters to be optimized are the orientations and the excitation current vectors. An objective function f, defined only for the x and y magnetic field component, is used to estimate the suitability of each dipole solutions. PSO is adapted to our system of nonlinear equations, and the optimization is carried out in MATLAB. Pending the optimization process, the stability of the dipole solution is enhanced over time instant, and PSO minimizes the objective function from 0.11 to 0.02 within 150,000 function evaluations. This is maybe time consuming, but the extracted US PSO model has a high level of accuracy with a minimum total error of 0.02, which is 69% lesser than the total error of the dipole model extracted from the first optimization level. However, the search complexity taken by PSO can be significantly reduced by using a small number of iteration and population size. as shown by this figure, where a very favorable dipole solution that minimize f to 0.05 can be found in only 12,500 function evaluations. The acquired results proves that with PSO, a high level of accuracy can be achieved whenever necessary by using a large number of iteration and population size. However, this comes at the cost of increasing research complexity. Therefore, it is suggested that the PSO control parameters be determined based on the required accuracy of the characterized applications. The optimized OS PSO model is simulated to calculate its magnetic field distributions. The comparison results at 3 mm are presented in this figure. As evidenced by this figure, a high level of accuracy is obtained with the US PSO model for the near field predictions, with minimum error values are obtained for the 3 magnetic field components. To inspect the validity of the composite model for the far field predictions, the comparison is also effectuated for 2 other elevations, namely 13 and 43 mm. At the high of the 13 mm, we can clearly see that the accuracy of the field prediction is notably enhanced compared to the conventional dipole model, with tolerable error are acquired for the 3 magnetic field components. A good agreement is also obtained at the high of 43 mm. However, at this elevation, the differences in the field amplitude level are somewhat amplified, especially for the Z component. The reason why more errors occur in the normal component is owing to the fact that only tangential magnetic field components are used in the equivalent dipole model extraction. However, although these differences in the field amplitude level increase, they are considered not excessive, and the model still gives good results. In order to show the accuracy improvement established by PSO, a comparison between the OS model extracted from the first optimization level and the improved OS PSO is also provided for 3, 13, and 43 mm. Comparison results at 3 mm shows that both models are considered to give good results at near plans above the device under test. Notwithstanding, the proposed approach seems to be more efficient, and the radiated field is correctly predicted using it. This becomes obvious at far plans such that 13 and 43 mm. At these plans, the amplitude and profile of the modeled fields obtained in the US model are critically deteriorated and dispersed. Meanwhile, the profile of the modeled fields obtained using the US PSO model still show good correlation. As evident from the error evolutions, the error value of the OS model are significantly increased and exceed 2 to reach 2.12. Meanwhile, in the proposed approach, the differences in the field amplitude level are somewhat higher, but still reasonable, and the total error acquired for the 3 magnetic field component is less than 1.33. Indeed, the obtained results demonstrate the effectiveness and practicability of the US PSO model in modeling the radiated emission of large-sized devices using as few dipole as possible. In this scientific contribution, an efficient US PSO model is proposed to correctly predict the radiated emission from any target device under test in the near and the far field regions. With the thesis objective in mind, the research work begins with a review of the most widely used radiated emission models, in order to select among them the one that partially meets our needs so that we can improve it. 2 of these models have been found of great interest, namely the infinitesimal electric dipole model and the plane wave spectrum theory. Keeping the principle of both model unchanged, our choice was to perform a comparative study beforehand in order to select to highlight their main limitations so that we can make improvement to overcome them. Based on the findings derived from the comparative study, we have incorporated several mathematical improvements into the conventional dipole model to enhance its modeling capability. As a result, a more versatile, stable, accurate, and improved equivalent dipole model called OSPSO is introduced. The proposed OSPSO model is applied to provide an equivalent source representation of a large-sized patch antenna. We have demonstrated with the obtained results that the proposed approach can correctly handle large-sized devices compared to prior models which suffer from performance degradation as the dot becomes large. Using only 1/3 of the dipole number, numerical results shows that the error values introduced in the improved model are much smaller than those introduced in the conventional dipole model, especially at near distance of both the device and the test. Therefore, an excellent approximation for the field distribution created by the antenna at near and far distance is achieved using the OSPSO model. What's more is that with PSO, a high level of accuracy can be achieved whenever needed, which is practically useful for the better localizations of noise sources and electromagnetic interference investigations. At the outcome of the research work done, several promising perspectives could be envisaged as the continuity of this research. The first perspective, which is in the modeling aspect, would be to provide a fully automated modeling procedure without user intervention, which would further reduce the number of dipoles. This would be accomplished by employing an image processing algorithm to detect regions with significant field values and thus determine possible dipole positions, orientations, and lengths. Then another algorithm is introduced to analyze the retrieved dipole to either split very lengthy ones or merge two or more very small neighboring ones if they have approximately the same orientations before passing these dipoles to an optimization algorithm. The second perspective, which is a continuity to the first one, would be to develop a graphical user interface with an option to estimate the field to transmission line coupling. Finally, we would also like to pursue our research on the development of this radiated emission model in order to achieve high accuracy in predicting the behavior of radiated electromagnetic field at the farthest possible distance of both a device and the test. And thank